Hey guys, today I'm going to show you liquid hydrogen sulfide synthesized by hydrolysis of aluminum sulfide, which is produced as a result of an ordinary aluminum and sulfur interaction. In the lab, aluminum sulfide is used as a solid source of pure hydrogen sulfide, because on additional water to it, it produces high-purity hydrogen sulfide. Here you can see the water boiling during the reaction and hydrogen sulfide forming along with water vapors, which then enters a drying tube with calcium chloride and condenses in a liquid nitrogen trap. Liquid hydrogen sulfide is a transparent liquid that boils at -60 degrees Celsius. It's quite interesting that despite the ventilation hood running at full power, plenty of common green bottle flies came flying in the lab during the synthesis. I've managed to capture these flies flying on my high-speed camera. The thing is, one of the characteristics of these flies is their quick reaction to the presence of dead bodies, and hydrogen sulfide is one of the gases that form during body decay. Liquid hydrogen sulfide is a highly flammable liquid that burns with a pale blue flame. However, if we add liquid oxygen to the burning hydrogen sulfide, the blue flame will become brighter. When the reaction stops, you can clearly see formed elemental sulfur. A stream of oxygen aimed at the pale blue flame of the burning hydrogen sulfide will also make it brighter. If we move the hydrogen sulfide flame across a water surface, we'll see the formation of peculiar patterns of sulfur due to incomplete oxidation. If the same flame is being moved across a fuming nitric acid surface, it will become brighter, and brown vapors of nitrogen dioxide can be seen forming along with sulfur. Bubbling hydrogen sulfide through concentrated nitric acid results in the formation of large amounts of nitrogen dioxide. On contact with fuming nitric acid, liquid hydrogen sulfide ignites with a pale purple flame. It reacts the same way with dinitrogen tetroxide. Being a very strong oxidizer in liquid state, osmium tetroxide produced a lot of brown powder in the reaction with liquid hydrogen sulfide. Of all possible products of this reaction, the only product that can have this color is osmium oxide 3. This test tube contains chromyl chloride. If we pass hydrogen sulfide flow through it, we'll see green smoke, which is the result of chromium trichloride being produced. Bear in mind that anhydrous chromium chloride is purple, but it turns green instantly during the reaction due to the formation of water. Liquid hydrogen sulfide ignites on contact with chromyl chloride. A peculiar reaction occurs when hydrogen sulfide flow is aimed at iodine monochloride. Hydrogen sulfide easily reduces iodine to elemental iodine, the purple vapors of which we can see during the reaction. Iodine, forming on an iodine monochloride surface, prevents further reaction. However, iodine is easily soluble in iodine monochloride, so the reaction goes on as soon as iodine dissolves and lasts until all the iodine is reduced by hydrogen sulfide. Some solid oxidizers are also able to ignite hydrogen sulfide. Lead dioxide is one of them. As a result of a violent reaction, we can spot not only black lead sulfide, but also orange red lead. Sodium and potassium peroxides are able to ignite not only liquid hydrogen sulfide but also its vapors. The aqueous solutions of the salts of some elements that produce insoluble sulfides, such as silver, cadmium, lead, are able to do that by reacting with hydrogen sulfide at a significant distance. Notice the quality of the mirror formed from lead sulfide. And here I got the expected yellow precipitation of cadmium sulfide. Divalent tin solution can also react with hydrogen sulfide at a distance and produce brown tin sulfide. The reaction of selenous acid with hydrogen sulfide is quite interesting too, as it results in the formation of two elements at once, the yellow sulfur and red selenium. I also expected the reaction between liquid hydrogen sulfide and cobalt trifluoride to be violent. But it resulted in cobalt trifluoride, just reducing to cobalt difluoride. The reaction is more visual when performed with gaseous hydrogen sulfide. And now I have a question for you. The reaction between mercury dibromide and hydrogen sulfide that leads to the formation of mercury sulfide is known. But notice the way mercury dinitrate reacts with hydrogen sulfide. It turns green the flow of hydrogen sulfide as instantly as it turns white again the moment we remove hydrogen sulfide flow. So the question is, how do you explain that? Thanks for watching, guys, hope you enjoyed, and I want to take a moment to express my sincere gratitude for your support, my dear patrons. I couldn't have done it without your help. Thank you for supporting my work and allowing me to share my love for chemistry with you. I appreciate each and every one of you, and I'm grateful for your continued support. See you in the next video.